In this lesson, we're going to talk about some of the trends that exist within the periodic table. The first one we're going to talk about is atomic size. The size of an atom is measured in terms of its radius, and the radius of an atom is the distance from its nucleus to the approximate outer boundary of the cloud-like region of its electrons. And you can see that in the diagram. And so the size of an atom is determined by how many protons it has and how many electrons it has. So when we're explaining the trends that exist, we're going to be considering those things. How many protons are there and how many electrons? So this is what the periodic table would look like with the size of the atoms shown. So you can see the trend is that as you go to the left, the atomic radius increases, and as you move down the periodic table, it increases. So if we start by looking at what happens when you move down the periodic table, so the trend is that as you go down, the atomic radius increases. So why is that? Well, as you go down a group, the electrons occupy more energy levels. Right? As you move down each group, there's one more energy level. So because the energy level is further away from the nucleus, those electrons are further away, so the atomic radius increases. Now, if we look at the trend going to the right, so as you go across from left to right, the size of the atom decreases. So why does that occur? So we know that within a period, the elements all have the same number of occupied energy levels. But what happens as you go across a period, the amount of positive charge in the nucleus increases because the atomic number is going up as we go across. So there's more protons pulling in on those electrons. So because there are more protons pulling the electrons, they pull them in tighter and the atom gets smaller. The next trend we're going to look at is ionization energy. So this is the amount of energy that would be required to pull one electron away from an atom or an ion in the gaseous state. And so we're pulling away an electron. And it's those valence electrons that are most easily removed, right? They're going to be the one that's removed is going to be a valence electron. So really, you can think of ionization energy as a measure of how tightly those valence electrons are held. Right? So if an atom is happy to give away an electron, it's going to have a low ionization energy. The valence electron is not held very tightly. Whereas atoms where it's more difficult to remove an electron, they're holding on really tight. Those are the high ionization energies. So we explain these trends that we're going to talk about in a minute based on the force of the electrostatic attraction between the protons in the nucleus and the valence electrons. And that force of electrostatic attraction is determined by two factors. So the first is the effective charge of the nucleus. So we're going to take a little sidebar here and talk about what that means, effective charge of the nucleus. So if you think about the atom, we have the nucleus in the center and the electrons around the outside. The electrons that are on the outside, the valence electrons, are going to be attracted to the nucleus, but they're also going to be repelled by other electrons that are in the way, that are in between it and the nucleus. So those valence electrons are shielded from the full nuclear charge. They're not feeling all of the nucleus's charge. What they're feeling is the effective nuclear charge. And so you can calculate that by subtracting the number of inner shell electrons from the number of protons in the nucleus. So as an example, if you were to look at sodium, so we know sodium has 11 protons, and 10 of its electrons are in inner shells. So its one valence electron is being shielded from the full charge by 10 inner electrons. So it's really only feeling a charge of +1. Okay, so that's the effective nuclear charge. And so that is going to determine how tightly the valence electron is held, right? If the effective charge is larger, there's going to be a stronger attraction. And the other factor that is determining this force of electrostatic attraction is how far those valence electrons are away from the nucleus, right? A larger distance away means a weaker attraction. So the trends for ionization energy are the opposite of atomic size. As you go up the periodic table, ionization energy increases, and as you go across to the right, ionization energy increases. So if we look at those separately, so as you go down, ionization energy decreases. Okay, so why is that happening? So we have to think about those two things, the effective nuclear charge and the distance of the electrons from the nucleus. So if you go look in one group, all the elements have the same effective charge. Right? Sodium, we talked about, has an effective charge of 1. If you move down to potassium, it has 19 protons and 18 inner shell electrons. So it also has an effective charge of 1. So that's not what determines it, because it's all the same all the way down the group. However, as we've talked about previously, as you go down the group, the electrons are getting further away because there's more occupied energy shells. So because they're further away, they're less attracted to the nucleus, which means it's easier to remove that electron. Then if we look at the trend heading to the right, ionization energy is increasing as you move across the period. So again, we need to think about those two factors. So we know that elements within the same period have the same number of energy shells containing electrons. So the distance doesn't change all that much, not dramatically. However, as you're going across the period, the effective nuclear charge is increasing. So the valence electrons are being more strongly attracted to the nucleus. And that's pulling them in tighter, as we talked about, holding them tighter, so then it's harder for them to be removed. So as an example, if we look at sodium again, right, we've shown that that has an effective charge of 1. And then if you go to the far end of that period and look at chlorine, well, it has 17 protons, but still only 10 inner shell electrons. So it has an effective charge of +7. So all of its valence electrons are being pulled in by a charge of 7, whereas sodium's is only being pulled in by a charge of 1. So chlorines are harder to remove. The next trend we're going to look at is electron affinity. So this is a measure of the change in energy that occurs when an electron is added to the outer energy level of an atom to form a negative ion. So ionization energy was pulling electron out. Electron affinity is adding electron. So the values here are a little different because negative is actually higher, right? So a negative value for electron affinity means that energy's been given off when that electron was added. So if you have a high negative number, that's a high electron affinity. Whereas if you have a positive value for electron affinity, it means energy was required to add that electron. The atom needed not only the electron, but you had to give it more. You had to say, here, have some energy too. That was the only way it would take the electron. So when you've got really low negatives or positive numbers, this is a low electron affinity. So the trends are somewhat irregular. They're not quite as clear-cut as the other ones, but there are still trends. In general, metals, so on the left of the periodic table, have low electron affinities. And this makes sense because metal atoms prefer to lose electrons. They really don't want any more. They prefer to lose electrons and form a positive ion. So they're not going to have high electron affinity because they don't want an electron. Whereas nonmetals have a higher electron affinities because they want to gain those electrons to become stable and form negative ions. The noble gases on the very right also have very low electron affinities because they're content just the way they are, right? That's why they're the noble gases. They're stable. They have full outer valence shells. So they don't want electrons either. So we can summarize that in general. As you go down a group, the electron affinity decreases. As you go across the period from left to right, the electron affinity increases. So on the periodic table, it increases as you go up and increases as you go to the right. Same trend as with ionization energy, except there's an exception. The noble gases, their electrons affinities are low, right? So even though the electron affinity increases as you go to the right, once you hit those noble gases, it drops back down and they have low electron affinities. And finally, the last one we're going to look at is electronegativity. So this is a measure of an atom's ability to attract shared electrons in a covalent bond. So you might recall that in a covalent bond, right, atoms are going to share their valence electrons so that they can have a full outer energy level and be stable. So we're looking at how tightly the nucleus can hold those shared electrons, right? So we can also explain these trends by that electrostatic attraction between the nucleus and the valence electrons, which again depends on those two factors, the effective nuclear charge and the distance from the nucleus to the valence electrons, which has to do with the number of energy levels. So as you go down each group in the periodic table, the electronegativity decreases. So why is that? Well, the valence electrons, which are the ones involved in bonding, are further away, right? They're getting in farther and farther energy levels. So because they're further away from the positive charge, the atom is less able to attract them. And as you go across a period from left to right, the electronegativity increases. And this is, as we've previously described, the effective charge of the nucleus is increasing. So the nucleus can better attract those bonding electrons. There's also an exception here. The noble gases don't form covalent bonds. They don't share electrons. So they just don't have electronegativity values at all. They just don't exist. So we can summarize that. As you go up the periodic table, electronegativity increases. And as you go across to the right, electronegativity also increases. And again, there's an exception with the noble gases in that they don't even have electronegativity values. So we can put all four of those trends together. Right? So we start with atomic size or atomic radius increases to the left and down. And then the other three are all the opposite. So they increase as you go up, the ionization energy, the electron affinity, and the electronegativity, and then they increase as you go to the right.